This video is a continuation on traveling waves. We're going to go over a few more definitions, but primarily we're going to look at what happens when two waves interact with each other. Before that, we're going to make some of the connections to music because waves and music go hand in hand. And for those of you musically inclined, this may be your either the most fun unit because you relate to it, or the worst unit because all of a sudden it takes all the fun out of music. Okay, so the speed of a wave is solely dependent on the medium that the wave is traveling through. Now, to change the speed, I have to change the medium. There are different aspects of the medium that I can change, but what I need to think about is simply that the medium needs to change. So the speed of sound through air is pretty much the same. But if I change the density of the air by changing its temperature or the pressure in it, then the speed will change as well. In general, we use the speed of sound as around 340 through air. And for the speed of a wave on a string, we're going to look at that. Okay, because the two things that the speed depends on is, one, the tension in the string. Okay, and that's what we change for those of you who play a string instrument like a guitar or a violin, when we change the tuning pegs, what we are changing is the tension in that string. We're not changing the length of the string, it's pretty much defined by the instrument. We're changing the tension. Okay, and by changing the tension, I'm changing the speed of the wave on the string. Okay, and we'll also look at how that changes the frequency. The other thing that makes a difference is the density of the string. Okay, that's what M over L on the bottom of that square root sign is. Okay, the density of the string, or the linear density of the string. That's why if you look at the strings on your violin or a guitar, the lower the note, the thicker the string. Okay, the length of the string is pretty much the same regardless. Okay, especially on a violin. On some guitars, it's especially electric guitars, some of the notes may have a different wavelength, but for the most part, the length of the string is the same. And so by changing the density, I can slow or speed up the wave. Okay. The next thing we're going to talk about is what happens when a wave hits an end, or it changes its medium effectively. Okay, when a wave hits the end of something, it tends to reflect back. Okay, that's what basically a sound hitting a wall is. Okay, that's an echo. Light, remember, is a wave, and when light hits a mirror, it reflects back, and I can see myself. Okay, sometimes you can see it when in a water wave, when water hits the edge of a bowl, it bounces back. And so that's wave reflection, and that's going to be very important to help us set up music and standing waves in the next set of slides. Okay, but what happens when the energies of two waves collide? Okay, I'm going to switch over to a simulation for now, but what's important to realize is that the amplitudes add together when two waves collide. Okay, so here's a wave going on a string. Okay. Whoops, let's reset that. Okay, and let's slow it down. Okay, so here's a wave going on a string, and we can see what happens when it hits the other end. It reflects back on the other side of the string. Okay, and so that's fine, but let's see what happens when I have two waves coming back and intersecting with each other. Okay, so I'm going to start another pulse here. Okay, and right before they collide, let's see what happens, okay? And I'm going to see if I'm going to step one step at a time, okay? And you can see as the two waves collide, they effectively cancel out because the amplitudes add together, okay? And then if I continue, the energy of the waves continue on. They don't bounce off of each other. They continue and pass right through each other. Okay, I'm going to reset that again. Let's go back. There, slow it down a little. Okay, and here's my pulse again. And actually, I'm going to change to a loose end because I want to show you what happens when they meet on the same side. Okay, so here's my pulse. Okay, whoops, loose end. Okay, so there's the pulse and it comes back on the same side. Okay, so I'm going to send another pulse right here, and right before they collide, okay, look at how much bigger that wave is when they collide. Okay, and if I continue on, the individual waves are about half the size. Okay, so that's what I mean by showing that the amplitudes add when the energies of two waves collide. And this adding of the amplitudes is called superposition. Okay, anytime the two waves collide, the energy of the waves add together and then continue on. They don't bounce off, they don't end. The energy just keeps going. There's no result of that collision, okay, after the waves pass through. Okay, a couple more definitions, okay. Interference is going to be when two or more waves collide. Okay, constructive interference is when the collision results in a larger amplitude wave. That's what happened when we had two waves on the same side. Destructive interference is when the collision results in a smaller amplitude. And that's what happens when the waves were on opposite sides. You ended up with zero at that point. Okay, and so a couple more definitions are antinodes and nodes. We'll see those more in the next set of slides, but an antinode is the point of maximum constructive interference. Okay, the greatest movement. A node is a point of maximum destructive interference, or effectively no movement whatsoever. Okay, and so the principle of superposition says these amplitudes are going to add together either constructively or destructively. Okay, so in a constructive interference case, we'll end up with bigger waves, and in a destructive interference, we'll end up with smaller waves. Okay, the two waves should have the same amplitude. If my resulting amplitude is zero, it's just that they're offset from each other. Okay, thank you.